Jacqueline. We are students a part of the ACT Lab, and we were assigned a year-long project in which we conduct a synthesis and characterize what we synthesize, a kinetic study, and a quantitative study. For our project, we are enzymatically synthesizing a cocoa butter equivalent using oils as well as quantifying fatty acid methyl esters in chocolate products. To briefly introduce our project, the reasoning behind our study is that as the demand for cocoa butter increases, the world supply of it falls due to unfavorable climatic conditions. So in order to produce a substitute, cocoa butter equivalent can be made from restructuring the triacylglycerols or tags found in oils. We are working with olive oil and palm oil, and we will be targeting 5 main tags. Chocolate fats mainly come from cocoa butter, which contains 3 fatty acids, palmitic acid, stearic acid, and oleic acid. To further analyze cocoa butter for our quantitative study, we targeted these 3 fatty acids and methylated them into fatty acid methyl esters, or FAMEs, to quantify.
For the quantitative study, the objective is to quantify the fatty acid methyl esters of the main fatty acids found in milk, white, and dark chocolates, the main fatty acids being palmitic, stearic, and oleic acid. These 3 contribute to the overall flavor and texture of the chocolates. We hypothesized that between milk, white, and dark chocolates, dark will have the highest fatty acid content due to it containing more cocoa. This study was done by taking 2 grams of each chocolate, letting it mix with hexane and isopropanol for about 4 to 5 days. Aqueous sodium sulfate was then added to this. The organic layer containing the fatty acids was then extracted from this mixture and turned into fatty acid methyl esters, FAMEs, using KOH as seen in the schematics. The FAMEs were then diluted and run on GCMS.
So for our results for our quantitative study, we developed a calibration curve using a FAME standard and used this to successfully quantify methyl palmitate, methyl stearate, and methyl oleate in our chocolate products. We found that dark chocolate contained higher concentrations of these FAMEs, and this supports our hypothesis.
Okay, so for the procedures of our synthesis, our objective is to synthesize cocoa butter equivalent. We first began with equilibrating our enzyme in a saturated sodium chloride solution, and after a day, it was ready to be put to use. We then measured out 40% of the palmitic acid and 60% of the stearic acid to make our palmitic stearic fatty acid mixture, or PSFAM, with multiple ratios ranging from 1:1 to 1:5 of the oils to PSFAM, with increasing PSFAMs and 10% of our enzyme all loaded in a dram vial before it was set to incubate in the orbital shaker.
Now into synthesis schematics. Oils are composed of tags which have varying fatty acids such as palmitic, stearic, and oleic acid in varying SN1, SN2, and SN3 positions. These tags are then reacted with PSFAM, which is catalyzed by the SN13 lipase under 60 degrees Celsius at 160 RPM, which then produces the CBE, the POS tag.
So to characterize our synthesized samples, we decided to utilize a gas chromatograph with a mass spectrometer, as well as differential scanning calorimetry. For our GCMS method, it is not finalized as we are currently developing one, and displayed here is a potential method that we have not tried yet, but we are considering. We are considering this method because with the RXI PAH column, due to its unique high diphenyl content as well as its small film thickness, these conditions are suitable for analysis of tags.
As for the characterization, DSE was used as a thermoanalysis for a natural CB. For the method, it was brought down to negative 40 degrees Celsius, then brought up at a rate of 10 degrees Celsius per minute to 80 degrees Celsius, which is then held for 15 minutes, which is then brought down to room temperature. Onto the results for the synthesis, both the DSE and the melting point apparatus were used. Only the CB standard was ran in the DSE, and the endothermic peak showed that the melting point was at 37.81 degrees Celsius, which agrees with the literature. The melting point apparatus was then used to determine the melting points for each oil at different ratios. The only one that falls within this range is the 1:3 olive oil sample as predicted from the literature. As for the GCMS data, the method is still being developed, as Hala mentioned, due to no peaks being visible as of now.
Okay, so for our kinetic study, it is all about finding our rate of change in the tag composition. The ratio that we chose to run for our kinetic study is the 1:3 olive oil because when using the melting point apparatus, this ratio was the closest to our natural cocoa butter, which was determined by DSC. The tag that we are targeting is 1-palmitoid 2,3-dioleoglycerol because this has the highest percent convergence out of all of the other tags. Beginning our study, we prepped our 1:3 ratio and placed it in the incubating orbital shaker. For the kinetics, the time intervals we decided on will range from 5 to 320 minutes, which each of these timestamps being doubled into the next, and we will analyze the ratio on GCMS in order to finally determine our rate of change. Since we do not have a standard to compare or refer back to, what we will do is take these chromatograms from GCMS and layer them onto one another to see how our peaks are affected, such as how they shift, where they shift, and such. Overall, continuing to future works, we still have yet to run our ratio on GCMS after each particular timestamp in order to get results for our kinetics, and as Hala mentioned, we still have yet to finalize a new method for our synthesis.
And that is all. We would like to thank the ACT program as well as those who have helped us.